Right, so let's look at vector addition. We will first explore these ideas in one dimension, and thereafter we will move to two dimensions. So let's consider vector addition. Consider that you have two vectors, v1, which is 2 units to the east, v2 is 3 units east. Remember that vector is a quantity that has magnitude and direction. So we have the compass here, where we have north, which points upwards, and south points downwards, west points to the left, and east that points to the right. So v1 and v2 both both directed eastwards. So what will be the result of adding v1 and v2, given that v1 is 2 units east and v2 is 3 units east? So let's go to this number line here. So you can see that I draw v1 as being 2 units, and then v2 is 3 units from 2 to 5, that is 3 units. So the results of this is a vector that is 5 units east. So this is a calculation. VR is v1 plus v2. Add the magnitudes, 2 plus 3 units, and the direction is east. And then that gives us 5 units east, as we have seen in our diagram. So that is our resultant vector there. So what is a resultant vector? A resultant vector is a single vector that has the same effect as the combination of 2 or more vectors. That is to say that this red vector here is a resultant vector. It has the same effect as the combination of v1 and v2. VR is equal to v1 plus v2. And I will also demonstrate this. This also works the same way, even if we had these vectors pointing to the north. So we would apply the same principles there. So if you have v1 is 2 units north and v2 is 3 units north, then VR is going to be 5 units north. And that is our resultant vector there. Let's look at vector subtraction. We have information here. Let me specify that east is taken as positive. So v1 is a vector with a magnitude that is 5 units, and the direction of v1 is east. v2 is a magnitude of 3 units, and the direction of v2 is east. What we want to determine is difference, or what is v1 minus v2. In this number line, I draw vector v1, which is 5 units east. And then let's draw v2, which is 3 units east. What is v1 minus v2? I think you can see from the diagram that when you subtract v2 from v1, you'll be left with a vector that starts, let's say, from 3 to 5, which is a vector that is 2 units. So the vector v3 is 2 units to the right. That is v1 minus v2. Let's look at the calculations for that. v3 is equal to v1 minus v2. That is 5 minus 3 units east, and therefore v3 is 2 units east. Note that the expression v3 is equal to v1 minus v2 is equivalent to v3 is equal to v1 plus the negative of the vector v2. Let us demonstrate what that means. So if I have V1, that is 5 units, then V1 minus V2 is the same as V1 plus the negative of V2. So that is my V2 there. And then that is my negative of V2 there. It starts from 0 to minus 3. Now, if I add these vectors, what do I get? I get a vector that is 2 units to the right. Right? Let's look at another example. In this example, I have V1 that is 2 units east and V2 is 5 units east. So in this example, V1 has a magnitude that is smaller than the magnitude of V2. What will be the result of subtracting V2 from V1? So this is my V1, it's 2 units. And that's my V2, which is 5 units. And I said that when you subtract V2, it's equivalent to adding the negative of V2. Negative of V2 has the same magnitude as V2. So that's going to be 5 units. But the direction is going to be opposite to that of V2. V2 is east. Then the direction of minus V2 is west. When we add this, what do we get? The result will be a vector that points left, which is from 0 to minus 3. So V3 is equal to V1 minus V2. That's 2 minus 5 east. And that's minus 3 east. So there's a negative there. Negative indicates that we need to change the direction from east to west. Now let's look at the subtraction of vectors that are in opposite directions. Consider that I have V1, and I need to note that as well, that I'm taking east to be positive. So V1 is 2 units east and V2 is 2 units west. Now, what is V1 minus V2? So if I subtract V2 from V1, what do I get? So in my number line, let me draw V1 from 0 to 2, that's 2 units east. And V2 is 2 units west. Recall that subtraction, if I subtract V2, that is the same as adding the negative of V2. What will be the negative of V2? Negative of V2 is a vector that has the same magnitude as V2, but that points in an opposite direction. So the negative of V2 is 2 units east. Now if I add that to V1, then the result is 4 units east. Let's get the calculations. Calculations is V3 is equal to V1 minus V2. V1 is 2 units. Subtract V2 is minus 2. Minus times a minus gives us a positive, and 2 plus 2 gives us 4 units. So V3 is 4 units east. Let's look at one more example to emphasize the subtraction as addition of negative vector. So consider situation. I have V1 as 2 units east and V2 is still 2 units west. But now I want to subtract V1 from V2. So then V2 minus V1 is the same as V2 plus the negative of V1. So this gold vector there is the negative of V1. Since V1 is 2 units east, then the negative of V1 is 2 units west. And then the resultant vector there is going to be equal to 4 units west. V3 is equal to V2 minus V1, minus 2 minus 2, equivalent to minus 4. And therefore, V3 is 4 units west. Right, so let's look at how we can apply these concepts discussed so far in these following examples. So let's look at change in momentum. Change in momentum, which is final momentum minus initial momentum, that is equal to mass times final velocity minus mass times initial velocity, since momentum is defined as the product of mass and velocity. So let's consider that if we have a mass that is equal to 800 grams, we can convert that to kilograms, that is 800 over 1000, which gives us 0.8 kilograms. Assume that this mass has an initial velocity of 3.5 meters per second to the right, and then let's say it gains some velocity so that it has final velocity of 5.5 meters per second to the right. Now let's look at what is our initial momentum. We can interpret the initial momentum as the scalar multiple of the initial velocity. What that means is that if we have the equation that momentum is mass times velocity, well, the mass is a scalar quantity and velocity is a vector quantity. So then momentum is a scalar multiple of velocity. That is to say that you have the velocity of 3.5 meters per second to the right. Then the momentum that's associated with this velocity is 0.8 times 3.5. So this is our initial velocity. Then if we multiply this initial velocity by 0.8, we get the momentum. So that's going to be reduced since 0.8 is less than 1. So then our momentum is going to be 2.8 kilograms meters per second to the right. So that is our initial momentum as a scalar multiple of initial velocity. Similarly, into the same for the final momentum, it's a scalar multiple of final velocity. So if you have final velocity there is 5.5, then you can scale that by 0.8. So that gives us a momentum of 4.4 kilograms meters per second to the right. Okay, what about change in velocity? Change in velocity, delta, means final quantity minus the initial quantity. So delta V is V final minus V initial, which we can approach as adding the negative of the initial velocity to the final velocity. So V final minus V initial is 5.5 minus 3.5, and we can draw the vectors. We can start with the initial velocity, which is Vi, is the one that is 3.5 meters per second to the right. Negative of this velocity is minus Vi. It points to the left, but it has the same magnitude as initial velocity Vi. Then we add the final velocity. So when you add the final velocity and the negative of the initial velocity, you get the final velocity minus initial velocity. And from this diagram, we can tell that the resulting vector there should be to the right. So this is our resulting vector there. It is 2 meters per second to the right. So that is delta V. Delta V is 2 meters per second to the right. So this is our change in velocity. You can actually imagine adding this change in velocity, which is this 2, to the initial velocity there, that is 3.5. Then that will give you this final velocity of 5.5 meters per second to the right. Now let's look at change in momentum. So change in momentum is mass times final velocity minus mass times initial velocity, which is mass into V final minus V initial, and that is 0.8 into 5.5 minus 3.5, which is equal to 0.8 times 2. We can, at this step, note that momentum is the scalar multiplication of velocity. So the change in momentum is a scalar multiple of the change in velocity. So that is, the change in momentum is going to be this velocity delta v, which is equal to 2 times 0.8. So we can scale this change in velocity by 0.8, and then we get the change in momentum. So that is initial velocity, and you scale it by 0.8. That gives you the change in momentum, which is 1.6 kilograms meters per second to the right. That's equivalent to final momentum minus initial momentum. We already have these vectors there. So we'll approach this the same way we did with the change in velocity. We will add the negative of the initial momentum to the final momentum. 4.4 minus 2.8. Let us draw the initial momentum is pi, and the negative of this momentum is the vector that is same magnitude as pi, but points in the opposite direction to pi. So minus pi is 2.8 kilograms meters per second to the left. And when you add this to the final momentum, p final, this gives us p final minus p initial, which is our change in momentum. And the answer should be the same as 0.2 times, no, 0.8 times 2, that gives us 1.6. 4.4 minus 2.8 gives us 1.6. So the change in momentum is 1.6 kilograms meters per second to the right. Now let's consider an example where we have the magnitude of the final velocity being smaller than the magnitude of the initial velocity. We have a mass that is equal to 1.5 kilograms. Now let us go and determine the initial momentum. Initial momentum, we interpret momentum as a scalar multiple of velocity, and the initial momentum is scaling the initial velocity by 1.5. So that is 1.5 times 4, and that gives us 6. So then the initial momentum is 6 kilograms meters per second to the right. What is the final momentum? The final momentum, you scale the final velocity vector. So that is, you will scale 2 by 1.5. That gives us 3. That is, final momentum is 3 kilograms meters per second to the right. What is change in velocity? Change in velocity is v final minus v initial, which is 2 minus 4 meters per second. And do as we did in the previous example, consider this as adding the negative of the initial velocity to the final velocity. So that's v initial, then this is minus v initial, then you add v final, then the result should be v final minus v initial. And you can tell that the resultant vector here points to the left. So the resultant vector here is change in velocity is equal to 2 meters per second to the left. And you can consider adding this change in velocity 2 meters per second to the left, add it to the initial velocity of 4 meters per second to the right, and the answer to that is should give you v final, which is 2 meters per second to the right. Do the same for change in momentum. You can calculate that as 1.5 into 2 minus 4, will give you -3, which is the same as P final minus P initial, which is 3 minus 6, which is the same as adding the negative of the initial momentum. It's going to be minus Pi plus the final momentum there. That's the change in momentum, which is equal to 3 kilograms meters per second to the left. And note that the momentum is always in the direction of velocity, because mass is always positive. So then momentum should always be in the direction of velocity. And so the change in momentum is in the direction of change in velocity. So this delta P as 3 is the same as scaling delta V, which is 2 by 1.5. And then that gives us this delta P. Let's consider that we have velocities that point in the opposite direction. We have V initial is 2 meters per second to the right. The mass is still 1.5 kilograms. And we have V final as 2 meters per second to the left. So we'll do as we did before. The momentum, so the initial momentum is the scalar multiple of this velocity. So that would give us 2 times 1.5 is 3. The initial is 3 kilograms meters per second to the right. And then what is final momentum? Momentum is always in the direction of velocity first. So the final momentum is the scalar multiple of the final velocity vector there. So that's 1.5 times 2 meters per second to the left, which is 1.5 times -2. And then that gives us momentum of 3 kilograms meters per second to the left. What is the change in velocity? So the change in velocity is the final velocity minus the initial velocity. So that is our initial velocity VI. That's VI. And then when we add the final velocity, then that gives us the change in velocity is to the left, which is -4. So the change in velocity is 4 meters per second to the left. Change in momentum, we expect it also to be to the left and to be the scalar multiple of the change in velocity. So size of it should be 4 times 1.5, should be 6. 1.5 times -2, which is -6. In terms of vectors, we can have the P initial, and then this is the minus Pi. Then we add the P final. Then minus Pi has the same magnitude as Pi, so that is a 3. And the magnitude of P final is also 3. So we expect the resulting vector to be -6, or 6 to the left. So delta P is 6 kilograms meters per second to the left. Now let us see how we can apply what you've learned so far to analyze the motion of this bouncing ball here. Right, so we have this ball that starts from a particular height above the surface, and the velocity it starts with is 0. And then this ball goes down, and then when it reaches the surface, with the velocity v. And what happens when it hits this surface? When it hits this surface, we use Newton's third law. This ball exerts a force on this surface, Fb on S. Newton's third law states that if object A exerts force on object B, then object B simultaneously exerts an equal and opposite force to object A. So therefore, the force that the surface exerts on this ball is the negative of the force that the ball exerts on the surface. So we expect that if this is our FB on S, then Fs on B will have the same magnitude as FB on S, but it will be in the opposite direction to FB on S. That is, Fs on B is minus FB on S. If we assume that Fs on B, which is this force that the ball experiences due to this surface, is roughly 200 times larger than the weight of this ball, then we can assume that this force is responsible to change the velocity, to change this velocity that the ball has when it hits this surface to new velocity that this ball has when it leaves the surface. This red arrow is the initial velocity, and the light blue arrow is the final velocity, and the green arrow is the change in velocity. And from the previous example, we know that the change in velocity is v final minus v initial, which is same as adding the negative of v initial to the final velocity. So that will give us the change in velocity, which is the green arrow here. Right, and then as the ball goes upwards, the velocity reduces all the way to 0 when the ball reaches the maximum height. Okay.